All right, now we're doing 7Q Count the Ones. This is by Rodent Rabies, and 89% of people like it. The Hamming weight of a string is the number of symbols that are different from the zero symbol of the alphabet used. There are several algorithms for efficient computing of the Hamming weight for numbers. In this kata, speaking technically, we have to find out the number of 1 bits in a binary representation of a number. Thus, 10 will equal 2 because there's 2 ones in the binary representation of 10, and the binary representation of 21 will be 3 because there's, the Hamming weight of 21 will be 3 because the binary representation of 21 has 3 ones. The interesting part of this task is that we have to do it without string operations, so we can't just do dot string 2 and then a reduce, which would make this video so much shorter, but whatever. Anyway, so what we got to do is we got to realize some things, right? So every time it's odd, there's going to be a 1 at the end, okay? No matter what. So like you see here, it's 0. If this was the number 2, it would be 1, 0. If it was the number 6, it would be 1, 1, 0. So in binary, if it ends in a 1, it's odd. And we can use that to our advantage, because if we can somehow get this here, count the 1 here, get rid of it, count the 0 here, get rid of it, count the 1 here, get rid of it, throw away the 0 and count the 1 again, we'll be golden, right? And you know what? That's what we're going to do. So we're going to say function, instead of function, we're going to say const here. We're going to say Hamming weight equals x. And then we're going to say an arrow right there. So the question is, how do we get rid of this 1 once we've counted it? Well, guess what? These brainiacs have devised a thing called right shift operator, which returns the signed number represented by the result of performing a blah, 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 blah. Anyway, basically, let's take this junk out of here, this junk here out of here, so we can get unconfused. All right, let's take all this junk out of here. All right, so now let's say 1. Let's say 5, 1. So the binary representation is this, and this doesn't matter at all. All right, so if we shift over this 1, it'll give us 2, don't you think? Because we'll get rid of this one, put another 0 over here, right? And this is what will be left over. So let's see if that's right or not. Oh, it is. Cool. So if we do it again with the 2, oh, it's 1, and we can count that 1, can't we? So, and what do we know about odd numbers, right? Something divided by, something remainder operator 2. If there's a remainder, it's a 1, right? So let's do something, all right? Okay. Basically, we're going to use a little bit of recursion, which is the act of a function calling itself, to solve a problem that contains smaller subproblems. So if we do something like, let's say x remainder operator 2 to check if it's odd, plus Hamming weight of, let's say, x, and then we use that right shift to shift over the thing, shift the 0 off, or the 1, whatever, and let's say Hamming weight 1. Won't that do something for us? Test it out. No, it's the maximum stack call size succeeded. So something's wrong here. Maybe we have to do something when it hits 0. So this is a good start, because look, let's go over here. Let's say 21. Okay, 21 we know is 10101, all right? So we check it once. So we say 21. What are we trying to do here? We say 21 remainder operator 2 plus the Hamming weight. So the next one would be after this would be 1010 after we did the little shift thing, because we're doing like a recursion, right? So now we're doing 10101. So plus 10 remainder operator 2, which would be 0, plus, but then it would shift to, then once we shift it again, it would be 101, which would be 5. So we would do 5 remainder operator 1, remainder operator 2, plus, and then we get rid of that one, and it's 2, remainder operator 2, plus, and then we've got 1, remainder operator 2, which will be, and then we get to 0, and it'll just go off forever and 0 for forever, because it'll be 0 after that. So we've got, this is 0 and this is 0, so we've got 1, 2, 3. All right, so this works. So all we got to do is use a ternary operator now to get rid of that, to stop the thing when it hits 0. So the ternary operator is the only JavaScript operator that takes 3 operands: a condition followed by a question mark, then an expression to execute if the condition is truthy followed by a colon, and finally the expression to execute if the condition is falsy. And this operator is frequently used as an alternative to the if-else statement. So let's say if x exists, okay? If x exists, because if x is not 0, we could just, yeah, if x is not 0, we're going to do this, okay? But if it is 0, we're just going to return x, okay? So it's going to do that whole thing. It's going to, basically for 21, it's going to do this whole thing right there, basically. And then let's do a console.log. Let's do 21 here. What the H is that? Oh yeah, we weren't doing Hemingway. Let's bring the Hemingway over here. Give me just a second. All right, let's do a console.log Hemingway to 21. No, we don't need to do that. Anyway, that's basically how we do it. Let's see if this works. And it does. It does work. Awesome. Attempt it. All right, submit it. I was going to go a little deep in that rabbit hole. Basically, as you can see here, pretty much the exact same as this. Let's go to mine. Just me and these 3 people here. Best practice in my opinion. And we'll see you next time. Wait, no, very like it too. And we'll see you next time.